All right, good morning, everyone. Rob Atkinson, I'm president of ITIF. I want to welcome you to what I can guarantee is a fascinating and hopefully enlightening discussion and event this morning. We're really honored to be able to host Professor Michelle Simmons, who is from Australia. She is a professor of physics and director of the Center of Excellence for Quantum Computation and Communication Technology. And most recently was named Australian of the Year for 2018. And for those of you who follow that, a quite distinguished honor. But among the people in the past who've won that honor are Crocodile Dundee. So she's in very good company. Hogan, but I can't remember his first name.
Paul
Hogan, exactly. Professor Simmons is also, and for this conversation, one of the leading scientists in the world on quantum computing. She directs this center at University of South Wales, leads a team of more than 200 researchers at 8 Australian universities, who are developing a suite of technologies for quantum computing, information storage, and communications. Her research group is the only one in the world that can manipulate individual atoms to make atomically precise electronic devices. Her team also is leading the world in the race to develop quantum computer in silicon. So she also established Australia's first quantum computing company, bringing together representatives of government, industry, and universities in an $83 million consortium. And in July of this year, she was named. She was the first female quantum computing physicist to admitted to the Royal Society of London. So we're going to hear from Dr. Simmons, and then we'll have a little conversation about quantum and sort of where it's going and why now and all of that. And then we'll open it up at least for 20 or 30 minutes for questions. I did want to add, ITF just started coming up with this What Is series after Labor Day. What is AI? What is 5G? Et cetera. And we have what is quantum computing? I'm a little chagrined to give it to Dr. Simmons because, like, who are we to say what is quantum computing? But I asked her if she would edit it and tell us all the areas where we made mistakes. But anyway, it's back there if you're interested in it. So with that, Dr. Simmons, we'll hear from you, and then we'll have a discussion.
Thank you. So good morning, everyone. Thank you for coming along. I thought I would start really looking a little bit back in history and giving the sense of the technical changes that are happening in the world and why quantum is suddenly becoming very popular now. So I'm literally going to go back and put in context why quantum computing is suddenly very prominent in what you're hearing about, and then why there is a lot of technology that needs to be developed for this field to come to fruition. And so if we look back all the way back to the 1940s, you can see that computers originally started with vacuum tubes. They were very large systems, very, very fragile systems. And indeed, the first, I apologize, we couldn't get rid of the taskbar. The first ENIAC computer back in 1946 literally had tens of thousands of these vacuum systems in there, the valves that switched between digital 1 and 0 in classical computing. And people realized that to change one of those valves would actually take a long time. To find an error in one of those valves and change it out was sufficiently long that they were looking for other ways of designing computers. And the first kind of semiconductor device was back in 1947, which was the first transistor. And this really took it from a very large-scale system to now trying to integrate everything on what we call one monolithic chip, so everything on one chip together, rather than lots of different materials that had to come together, lots of wiring and pulling cables out. And so the first transistor back in 1947 was actually a piece of germanium, and it really switched between digital 1 and off states just by applying a gate voltage to a transistor that existed in a semiconductor material. It took roughly about 10 years to get what we call the first integrated circuit, so to get actually 8 different components integrated on one chip at that time. And that really set the scene. Both of those inventions actually won the Nobel Prize because of the impact they've had on the world today. Then they started to integrate lots and lots of components in a chip, and our first IBM computer was in the 1980s. So you can see the first transistor, 1947, 1980s, before it actually comes to some kind of fruition. And there's a path that you can actually plot as to how long it takes from the invention of some new technology towards some kind of commercial application. And indeed, there were commercial applications years before this in using calculators or hearing aids. If we now look at the computing field, you now have over 14 billion transistors on a silicon chip the size of roughly 2 inches squared. So, you know, humanity has come an awful long way to miniaturize the size of those individual components with time. And I think that's a testament to the engineers that have worked in the semiconductor industry for many, many decades. You can now have server farms, and these server farms are so big, they take so much energy that they're actually locating them in cold locations. So this is Facebook's server farm, it's up near the Arctic Circle. The heat generation from these systems is so great, they're actually locating them places where it's cold, so that they can help with the cooling of the chip and they don't have to pay for lots of air conditioning to keep those chips cold. And if you now look, this is a Samsung fabrication plant. It actually costs $14 billion. It's going up towards $20 billion to build that fabrication plant. So this is one of their latest plants that's coming out. It's the size of 400 plus football fields. So it gives you a sense. And you know, the engineering that's required to build the chips of the future, pushing down to the smallest length scales, is costly. It takes a lot of engineers, a lot of equipment. Individual components are roughly $50 million in there, and you have to build a whole fabrication plant that kind of size to keep up with the miniaturization of the industry. And so Gordon Moore is obviously very famous, the co-founder of Intel. He plotted out the size of individual feature sizes on a silicon chip as a function of time. And he really noticed this phenomenological law for many, many years. Going back to the 1970s, he started to see that basically the number of components on a silicon chip doubled every 18 months to 2 years. And as a consequence, he would plot, you know, literally as a function of time, what the feature size would be. And so you can see here the feature size on the bottom as a function of time. And as you extend out, you can see that if you follow Moore's law from that scaling law from the 1970s all the way through, eventually you get to the point where the smallest feature size is a single atom, and that was predicted to occur around about 2020 if you followed that law. As it turns out, we're starting to come off that law. It's actually very difficult to make devices smaller every year, but nonetheless, that law is what has dictated the industry. So trillions of dollars go in every year to try and make devices smaller and smaller with the hope that eventually you'll get to this length scale. But another thing happens. As you make devices smaller and smaller, suddenly they cross over from the classical age to the quantum age. And quantum physics starts to dominate their behavior. And it's kind of well known in the industry that every atom in that transistor counts. So if you move an atom a few locations within the transistor structure, then the turn-on voltage of that transistor change. And it's actually not easy to make them reproducibly anymore. And so you can see this is a 22 nanometer node. They're actually heading down to 14 and down towards 7 nanometers now. But essentially a transistor is just literally a piece of silicon material. It's got an oxide and then a gate, and you literally apply a voltage on this gate, and that turns the transistor from on to off. So you put a positive voltage, it sucks up the electrons, that turns the transistor on. Negative voltage pushes the electrons away, turns the transistor off. And like I said, there are 14 billion of these transistors now on a silicon chip. So it's pretty amazing. And so imagine taking a silicon chip and chopping out 14 billion times. That's the smallest feature size of the individual transistors. If you look at the end of this law, and this is really how the Australian team got into this, there were two things that when we decided we were going to enter the field of quantum computing, there were two things that we bet upon. One was we bet that the industry's been going for more than 50 years, and we're going to assume that all the technology they've got is going to help to push towards this length scale here. But the second one was actually silicon is a great material to build a quantum computer. And one of the ironies for me was in the 1990s, people were looking at what's going to be the material of the future. They started looking at different materials, be it gallium arsenide, graphene. They went away from the silicon material in the research in universities. And ironically, that was the time when the Australian team decided actually silicon is a great way to build a quantum computer. So we're going to come in and instead of working on this kind of trajectory down here, we're going to go to the end point up here and design and build and test devices where the functional element is a single atom. So that was our bet. Moore's law is going to continue, and at some point they're going to get towards the length scale where atoms are important, and indeed they'll understand how atoms come into play. But actually, if you look at the materials for building a quantum computer, you want an environment that protects the qubit but is manufacturable, and ironically we think silicon's the way to go. And so this is an example of some lithography in our labs where we've literally manipulated individual atoms. So you can see it's roughly 100 times smaller than the conventional silicon transistors. So let's just step. Yeah.
There's just a temperature in the upper right of the last part.
Yes. So this was the hope. Originally in the conventional silicon industry, it was viewed if you could make a device so small, you could actually operate atoms at room temperature. So at the beginning, what we're doing with the quantum computer, actually they're all millikelvin, so low temperature. But for conventional computing, you'd have to have it working at room temperature. So this is a different way of looking at this field, and this is again another reason why I think whenever you design new technology, it opens up whole new areas and whole new types of devices you couldn't build before. So we all know the light microscope allowed you to see things you can't see visually. So this is an onion cell. Now if we went down to, you see the length scale down here, so it's on the 0.1 millimeter scale. If you then develop the electron microscope, that allows you to see the world at a much smaller length scale. So taking that onion cell, you can actually now start to see the nucleus in more detail and some of the structure inside the cell itself. You can also look at the human hair, which is about 50 microns wide. What we're doing is taking the next level down. So we're taking a scanning tunneling microscope. So it's essentially the next level of resolution below an electron microscope. And it allows us now to see individual atoms. So this is a technology from the 1980s. It has a very fine metal tip. It allows you to scan that tip across the surface. And you know, it won a Nobel Prize because you can see atoms for the first time. But seeing atoms is one thing. IBM came along and they actually manipulated atoms with putting metal on a metal surface. That's another thing. But actually you can adapt that microscope not just to see the world at that length scale, but to put atoms in place. So that was our bet. Let's adapt that microscope so it's not just an imaging tool, but it's a fabrication tool. And what we're going to do is design devices where the functional element is going to be a single atom. So it's right at the end of Moore's law. And that allows us to now look at those quantum states in great detail. So let's just understand, why is quantum computing going to be different? So I know there's experts here probably listening to this as well, but for a very high level, why is quantum computing important? A classical computer is great, it works very, very fast, but it has to check one thing after another in quick succession. So if I was to write a telephone number down on a piece of paper, a classical computer would look through the directory and go through all the A's and the B's and the C's. If I wanted to go faster, I'd split the directory up and I have 2 computers. If I wanted to go faster still, I'd put 3 computers. In the quantum world, it's akin to looking at all the directories, all the names in the directory at the same time and coming up with the answer instantaneously. Now a lot of people don't like that, and it's a kind of simplification, but to try and understand how that works, the picture I'd like to leave you with is this picture of sitting, with the world. In the classical world, if you imagine now I'm in the quantum world, I'm a quantum bit or qubit, I'm at that atom, and I'm actually the spin on that atom. So I'm like a little bar magnet. You can put me in a magnetic field, I can point with the field or against the field. That's my 1 and 0 of quantum information. So there you go. 1 and 0 of digital information. So that's all we use in the classical world, those 1s and 0 states. But in the quantum world, I can point to anywhere on the surface of this sphere. And what that means is I can now write down an equation. So it's simple linear algebra. And what that implies is that I'm in some fraction of the down state plus some fraction of the up state at the same time. And this is only accessible in the quantum regime. It's called superposition. But essentially what I'm doing is I'm writing down one equation that describes that quantum state. Now the interesting thing about this is I need 2 classical bits of information to describe that state. So superposition is one of the fundamental principles of quantum mechanics. The second one, and I know this has fallen off the bottom and it's a bit tragic, is 2 qubits that are entangled. And so what you should see there is alpha 0, that's the component, and then it's a 0, 0, then alpha 1, 0, 1, alpha 2, 1, 0, and alpha 3, 1, 1. So you've got all those different components, up, up, down, 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 up, and up, down. And each one has its own fractional component at the beginning. So now I've got basically 4 classical bits of information to describe that one entangled quantum state. And so I want to step back. So this is the power of quantum computing. I now have one equation to describe my 2 quantum bit systems, but it contains double the amount of information from 1 qubit system. And if I perform any operation on this, such as you would in a classical computer, like a NAND or a NOT or a NOR gate, I perform it on all the individual states at the same time. So that's where the parallelism comes from. And so the key thing about a quantum computer is every time you add a qubit, you double the amount of information it contains, but you're performing the calculation of all those states in parallel. And so it's kind of predicted that if you get to a 30 qubit quantum computer, you would outperform a 14 billion bit classical computer. And if you could get to 300 qubits, it would be more powerful than all the computers in the world connected together. That's the kind of expectation of this field. So the race really is to try and get to that first stage, which is to demonstrate what we call quantum supremacy, the first demonstration that a quantum computer can outperform a classical computer. And it's roughly predicted around 50 qubits now. So how will that change the world? So there are, it is a very early field. There are a lot of algorithms that are coming out. There are a couple of very powerful ones in database searching and factorization that came out right at the beginning. But now there are over 50 different quantum algorithms. And they hit pretty much every industry that has large amounts of data or lots of variables. So you can see optimization problems. So you've got companies like UPS investing in this to try and work out the shortest distance for their drivers to travel. You've got machine learning on big data. So companies like Google looking at artificial intelligence, looking at defining understanding what is a person, what is a car for their self-driving cars. You've got quantum simulation, looking at different materials that are coming along, or looking at aircraft and how to optimize the design of aircraft of the future. And then you've got prime number factorization, which is really the code-breaking algorithm. So there are over 50 different algorithms that are registered now, and there's a huge amount of research in this space of what quantum computers can do. And so it's worth saying at this point that we're at the beginning stages of this. Those algorithms have not been demonstrated yet. And people are looking at building hardware now to realize some of these algorithms. So the promise is huge. And over the next 10 years, it's going to be very exciting for the hardware to develop. But ultimately, we need those near-term algorithms to prove the technology. There are lots of different ways that you can build a quantum computer. I've just got 5 here. There's probably a lot more than this internationally, but these are the kind of 5 leading contenders, and I've chosen those primarily because they have companies attached to them already. And so you've got silicon spin qubits, which is really what we're following in Australia. Superconducting qubits, you can see companies like IBM, Google, Quantum Circuits, Intel are following that. Ion traps, which is trapping an ion in a vacuum. Diamond vacancies, which is looking at a defect state in diamond, and then topological qubits, which is really what Microsoft is focusing on. So again, if you look at this compared to how the classical industry evolved, in the classical industry, everyone was focusing on silicon or germanium, and pretty much quickly switched from germanium to silicon systems. In the quantum computing world, there are many different ways you can make qubits. Each one of them have their own engineering challenges. Each one of them operate in different ways and under different conditions. So it's a very rich field of research at the moment. And I guess one of the great things about it is by pushing to application to try and find those near-term algorithms now, we're taking that technology that's right at the forefront in all these different materials and trying to see what's the best way to build it. And the reality is there may be more than one way to build it, and there may be different ways that the computer will operate. If we look at the silicon field, I talked about the fact that in silicon everybody kind of left silicon research because industry had silicon for so long. They were dominating what was happening in the silicon space, so university research went to different materials. Gallium arsenide was one of the materials they went to. It's a different kind of semiconductor material. When quantum computing came along, they very quickly realized we're going to adapt our material and try and build a qubit. And you can see to build a qubit, you've got to get down to 1 electron system. You've got to create a small component that you can encode information on. And that electron took them to about 2003 before they could make a device small enough to capture just 1 electron. In silicon germanium, again, universities were looking at this system in their research labs, and again, it took until 2007 before they could capture an electron system. What we're trying to do is to build a single atom system. So we've had to develop all the technology to make devices with atomic precision. And it's taken us until 2012 before we can actually make a single atom system. And like it says in the introduction, we're the only group in the world that can put a single atom in a silicon system and put information in and read information off the atom. And so really now for me, now's a kind of ticking time from our first transistor towards getting our first integrated circuit and then starting to look straight away at what applications we can do with our quantum computer that we're building. So this is just a very small scale of the silicon system. We're going to put a single phosphorus atom in. It's got 1 extra electron. We're going to encode information on the electron spin of that phosphorus atom. We put it inside essentially the same material that silicon industry uses. So it's a silicon substrate, and we have gate voltages. Put it in a low temperature and have a nice magnetic field. And there's all these different reasons why silicon's great. I know these are quite technical, but we can use the nuclear electron spins. They're very small systems. That means that basically have very high energy level separation between the up and down states. We can control them very well. They last a long time. They have very fast operation times. They're incredibly stable. And just by putting the atom in, we create the qubit by its very presence. So we don't need all these electronics around to create the actual qubit that we're making. They're very, very low noise. We've patented multiple architectures, but I guess the key thing is we're pushing all the technologies to fabricate with those technologies that are new, the scanning, tunneling, microscope, and then all the technologies of the cryogenics of operating it, and then the electronics to go for gigahertz frequencies, very fast frequency. All of that is right at the forefront of each of those fields, so we're bringing it all together to try and design this computer. This is what we're heading for. We call it a 10-qubit system. It is our equivalent to the integrated circuit, but with single atoms. And so our red things there are our phosphorus atoms. The blue lines are the electrodes that allow us to address them and put information in. But how do we do that? And so now I'm just going to go through the strategy, and it gives you a sense of why this field doesn't happen overnight. And hopefully you'll get a sense of all the equipment that we have to bring it together. So imagine we want to put 1 atom in place. The microscope actually works in ultra-high vacuum, so it's quite a technically complex system. So we can't see the device outside of the microscope. We've got to figure a way to see it once we put it in. We put these registration markers in that allows us to define the device. We put it in, we put down a layer of hydrogen. That acts as our atomic scale mask. And then we come along with this very black, that thing is our black metal tip, and we remove hydrogen from the surface, exposing the silicon underneath. We now want to bring in our phosphorus. We use phosphine gas. It only sticks where the hydrogen is exposed. So in such a way we can pattern into that top layer where the phosphorus is going to sit. And here we've got these, what we call lead states. This allows us to pass current through to our atoms. We then incorporate, so we do a chemical reaction. We get the phosphorus in the top layer of the surface. We then encapsulate with silicon. We can actually image where the phosphorus atoms are, so we know what device we've made. We then use those registration markers that when you take it outside, you can make contact to the outside world where you can actually visually see the chip. So you're using this microscope to do the atomic manipulation. You look at the chip, you can't see it, but we've got all these markers that allow us to find it and connect to the device. That's the actual first system we made. So back in 2002, we basically designed these two systems. It's a crystal growth system that allows us to grow the crystals, and a scanning tunneling microscope that allows us to manipulate the atoms. So it gives you a sense of the size of the system to actually build that chip. It was the first device we made in back 2004 using this technology. We proved that we could get something all the way through and find it. It wasn't a single atom, and it took us another 5 years to hone that technology to get to a single atom. When we put out that 8-stage plan, people came back and said none of those stages have been realized. So the chances of getting through all of the 8 and it working are very small. And so what's exciting for us is that year by year we have systematically knocked off every one of those 8 stages until we've got the device out at the end. But also, you know, not only have we got the strategy, but you've got the actual technology to actually build it. And this gives you a sense of the movie of how we make a single atom transistor. So there's our silicon chip with our registration markers. We put it in the ultra-high vacuum system, reconstruct the surface to get the atoms, bring down a layer of hydrogen on the surface that acts as our mask, come along with a tip to open up a hole on the surface, exposing the silicon underneath. We're now going to bring our phosphorus atom in, and we only want one phosphorus to go in. We bring pH3 in. It only absorbs where the silicon's exposed, and pH3 immediately dissociates to pH2, so we get 3 pH2s in that site. We then do a controlled chemical reaction, and what will happen is a pH2 will grab a hydrogen and come off, allowing another pH2 to dissociate. This pH2 will grab this hydrogen and come off, and now our single phosphorus atom, will reheat it up, will actually go into the crystal and kick the silicon out. So we can see that whole chemical reaction, and we get this ejected silicon telling us where the phosphorus has gone in. So that gives you the kind of level of control. We can place an atom in silicon with plus or minus 1 lattice spacing precision. We then encapsulate the silicon to provide that beautiful environment that protects our qubit. We're looking at that spin on that qubit. We want to make sure it's protected. But at the point we put the atom in, we also open up these leads where we heavily dope with phosphorus. And these leads actually behave like copper. So we can bring electrical signals right down to distribute our wave function to create the qubit states that we do. We then take the whole thing out of the vacuum and make contact to the buried device. So like I said, this is our 10-qubit system, first single atom transistor 2012. We found that we can make these leads all the way down to the atomic scale, and they behave like copper. It was not expected. We've then created these transistors that allow us to initialize and read out the spin state. So this is the kind of signature we get, very high fidelity, very high control of measuring the spin on that atom. So we bring a transistor in and we can measure whether it's spin up or spin down. We've now brought 2 atoms together. We get this process called entanglement. We can measure the wave function. We've got the kind of highest fidelity initialization and fastest measurements. We're looking at how to actually address each atom, so we can apply different frequencies and address one atom right next to the other atom, even though they're 10 nanometers apart, very, very close together. And we've designed these architectures for actually scaling this up to a full-scale architecture. So it's a whole new technology and a whole new way of making devices. And what's fascinating for me is we're looking at quantum computing, but it's also useful for making classical computers and indeed other materials. So it doesn't have to be silicon, it can be germanium. People have started looking at it with graphene and the same kind of technology. Just to give you a sense, the labs you need a full-on clean room to be able to do this technology. So here's just some various pictures from the clean room we have in Sydney. You need labs where you've got lots of scanning tunneling microscopes to be able to do this, to manipulate the atoms. And then you need these labs where you're cooling down the actual system to run at cryogenic temperatures. So, what does a quantum computer look like? Essentially, it's a system that looks like that. So it's about, it's not the size of the original ENIAC computer, but it's not the size of my laptop either. And so all of those technologies have to come together. And I guess one of the things we're very excited about is we can design, build, and test a device within 1 week. That's a very fast, rapid turnaround system. And what we've been doing in Australia is building the number of scanning tunneling microscopes. We now have about 6 or 8 of those, expanding that. And we're also building a number of dilution fridges to prototype. So we're up to about 20 different dilution fridges. But it's a very exciting time internationally. You'll hear lots about it, and no doubt the announcements over the last few days give you a sense. But if you look across the world, there's a huge amount of funding going in this area, whether it's the EU programs. Lots of different countries are coming to this. lots of different funding agencies are getting involved. It's something that has been going for a number of years, but it's really ramping up. And part of the reason it's ramping up is you're starting to see all these different companies come into this space. And I guess one of the interesting things for me is a lot of the national labs in the US are actually focusing on silicon. So silicon is becoming one of the commercially viable technologies for this field. It started out, a lot of it's superconducting qubits. These qubits are quite large. They've got the highest qubit number, but their coherence times are quite short. And in the long run, silicon has the promise of a longer coherence time and has that beautiful manufacturability. And so to that end, what we've done recently in Australia, we established this company. We've got a very unique model of that company. It's actually funded by government, university, and industry, co-investing in that company, and actually sits alongside what we call our Centre of Excellence, which has about 220 researchers. So the idea now is that we've got significant investment to build a 10-qubit prototype, but it's sitting next to a research environment where all the challenges of the research and development beyond that are working hand in hand with how the company's going. So with that, I'd like to thank you for your attention. I'm happy to sit and have a discussion and take questions. So thank you.
Well, that was great. I got about 84% of that, I think, so that wasn't bad.
That's great.
It reminded me of the famous Arthur C. Clarke quote, which is any sufficiently advanced technology is indistinguishable from magic. And what I mean by that is, when you think about how humans are going to progress, it's just about really understanding and figuring out really what nature, the secrets of nature.
Absolutely.
Extracting those secrets and figuring out how to manipulate them, and that's really what this is all about.
It is. It's really pushing, our understanding of the world to a different level and looking at it through a different lens.
Yeah, this is phenomenal. So let me ask some questions. A couple of questions here. One is there's two components to this, I think, that are critical. One is just is miniaturization. The first ENIAC was big. That's still pretty big, but not super big. And then the other is sort of cost reduction. You can imagine a system like that actually works, and you get up to 50 qubits, and it's amazing. But it's going to cost $60 million or something for each device. You'd still get a lot of deployment, but you're not going to get deployment at a small company, let's say. How do you think about the sort of predictions on that? And I guess the third one is power. So you have size, you've got power, and you've got cost.
Sure. So I think at the moment the big challenge for the field is no one's actually demonstrated an algorithm in the quantum space that can outperform classical unequivocally. So there's a lot of discussion about whether that has been realized. And I guess part of that is trying to understand the noise in the systems, how accurate they are, how pure they are. And so this technology is really designed at looking at that very fundamental. Take the purest system that you can make, get rid of all the variables that you have in materials, different qubit systems with lots of different material types. Try and make it fundamentally as simple as you can. So really, if you look at our computer, we've got two atoms, silicon and phosphorus, that's it. We have metal that's a long way away. We can grow silicon, so the surfaces are a long way away. And so we're looking at, can you control the world at that length scale? Can you mathematically model it? So one of the things we do is we measure the wave function. And from that, can you actually determine how entanglement works, and can you build a big enough system? At the moment, I guess one of the challenges for the field is if you go too big in qubit number too soon, but you don't really know what's happening at the microscopic or the atomic level, you're not really sure what you've got, yeah? And so our view at the moment is let's build it systematically, bit by bit, understand it qubit by qubit. If we control the world and we find that actually atomic positioning matters, or steps or defects matter, then we're going to find that out faster, I think. And so our approach is to do it, kind of the brute force, deterministic way, understand the world, at the same time mathematically model it as we build it. And that way we'll be able to understand how quantum computers can be built. And at the end of the day, if defects matter, you need to have that level of precision to be able to build the system that's going to work.
So how much of you sort of answered this question, I'm always interested in these questions of how much is just about brute force, progress over the technology, if you will, and how much of it is where you need ancillary things to get better. You talked about the tunneling microscope. Obviously, you couldn't do this without tunneling microscopes.
That's right.
Do you feel like sort of all the kind of components are pretty good and they're good enough, and it's just a question of you just figuring things out, or do components have to get better along with you?
So look, I think in the quantum field, we're pushing the technology, so those components are inherently getting better all the time. And I think one of the great things is by having those different approaches, people are having to get, some groups are having to get very low temperatures, so they're focusing on really good quality dilution fridges. We'll benefit from that. Other groups have to, they've got relatively fast qubits, they've got to get fast speeds down, so they're focusing on that. And so as all those technologies grow, we're all benefiting from each other's research. And that's what's great and, collaborative about the field in that sense. But fundamentally, I guess what's fascinating for me is we're at a point in human history where we have scanning tunneling microscopes, we've got cryogenics, we've got very fast, gigahertz frequencies. No one's put that together to make a device that didn't work in that way before. Mm-hmm. And so this is really what we're doing, is we're taking the leading edge of all those technologies and trying to create something that didn't exist and see what it can do. And there's that beautiful promise from the theoreticians that if you could control the world at this level, you've got this phenomenally powerful computer. And that's really what we want to find out.
So there was a study recently by Nick Bloom and who's at Stanford and John Van Reenen at London School of Economics, and they looked at the productivity of science over the last 50 or 60 years. In other words, how much a unit of input, meaning sort of scientific hours, let's just say, versus innovation or scientific advancement output. And what they found was that, really sort of troublingly, that the productivity of science is going down. And the reason is because the problems are getting so much harder. It was easy to do the first doubling of Moore's law. It's harder to do the last doubling. And in fact, they came up with an estimate that for every 1 hour of science time you had to do the first doubling of Moore's law. Today you need 70 hours to get the same doubling. So it's sort of the productivity has declined, if you will, by that much. So I have sort of two questions on that. One is part of this, we're sort of, as we jump into a whole new technology, the kind of productivity goes up because you're still, maybe I'm wrong, but you're still at low-hanging fruit. You're figuring things out that, oh, wow. So do you think that's true? And then the second question is, how much could the world accelerate quantum if we just decided to double funding for quantum? Could we? Does that speed it up, or are there just inherent sort of limitations?
Those are great questions. I think one of the things that I've seen, I'm fascinated with the history of the evolution of technology myself, so I've been reading lots of books, but I think now with the quantum field, you have to bring lots of different disciplines together. So, if you went back 100 years or 50 years ago, there were very few areas of discipline and you worked on your own and you brought people into it. Now, to build this, we do need mathematicians, we need engineers, we need physicists, chemists, all working together. So now the kind of barrier to entry is higher. So you've got to have big enough teams that work together cohesively and actually understand each other's language. Even though we're scientists, we don't, physicists and the chemists don't necessarily talk the same language. So there's that barrier, and I think what you'll see is there's going to be a period of time where everything seems to slow down as those teams build. But at some point, I think the output will start to come. I can't predict how that's going to happen, but it's a very different evolution to the way it used to be before. So I'm fascinated with that. And your second question, you have to remind me.
The second question was, if we were, I know you were
doubling the money.
You were in a White House meeting yesterday. There was a White House announcement from the administration, which was positive, that they're going to expand funding for quantum and have a more dedicated focus on quantum. Absolutely important. If all the governments in the world doubled quantum funding, would we have twice as much progress, or is it more half as much?
It's a fascinating question, because I think all fields at the beginning need funding to evolve, and so you've got to have at least a healthy base to start from. But then doubling the funding, it doesn't always get you double the output. And so I guess at some point, one of the things that we've learned in Australia is that collaboration at the beginning is critical, because you need those different areas to work together. You've got to build a big enough team, but you've got to get that collaboration working, and that takes time. It takes incentives, so those teams work well together, and those incentives will basically be dollars based on output. And so that's what the Australian system, I think, has done very well as. You can only win these big grants if you've demonstrated that you can work well together at the beginning. And so as a consequence, over the last 20 years, they've built these big research centres that have allowed us to have a phenomenally strong research base. And from that, you'll start to see, I think, now more and more companies coming out of the Australian system. But yeah, that's how I see it evolving. You need to get those teams together, break down the boundaries, which takes time, and then build where people are demonstrating output consistently in a high-value space.
Yeah, I mean, historically, academia has not been known for its ability to break down discipline silos. Chemists do chemistry and physicists do physics, and et cetera, et cetera. And obviously that happens when we focus on it. Do you think that's sort of an easy problem to fix if you just put money out there to encourage everybody to work together?
It's not easy. It is a cultural change. You know, I'm a firm believer that you need the depth in those disciplines, so you need to, really understand something at a very deep level before you can actually contribute to a collaborative program. So I do think you need those, but at the end of the day, if you want to build something, you need to bring them together. So there has to be incentives for that. But that said, research works well from the bottom up. So those people have got to naturally find each other and be motivated to do something together where they see the benefit from both sides. You can't just put money in and hope that's going to happen.
Sure.
But you have to, where it is happening, accelerator. That's my view.
Yeah. But you have to have departments that are willing to give benefits and advancement to scientists and researchers who are in this cross-disciplinary field.
Yeah, I think that's true. And I think, the other, a lot of researchers like to do fairly fundamental research. And in this area, it's really pushing the application boundary. And I firmly believe that you've got to push the applications for the fundamental research to grow faster. So again, that takes a change in mindset to reward those that are prepared to step out of their comfort zone and try these things.
Yeah. Yeah. So the famous famous book in science policy by an MIT professor named Don Stokes. The book was called Pastures Quadrant, and what Stokes was arguing is that there's this quadrant between sort of four-cell quadrant, basic and applied, and curiosity-driven versus sort of goal-directed. And he argued Pastures Quadrant is goal-directed but basic. And that's really what quantum is right now. It's really very basic early-stage research, but you're not just doing it because isn't this interesting?
That's right.
You're trying to solve a problem. You're trying to move forward. And that's historically been an area where the U.S. has been, I think, better than other countries. We've been willing to have missions around that.
Yeah.
Do you think that's the right way to think about this?
Yeah, I do. So I'm aware of that, and I certainly see ourselves in that category. But like I say, the applications drive the research, and so if you don't have applications, you will enjoy finding things, but it won't necessarily go anywhere.
Yeah.
And the applications really push it. How good is that? And so having a very focused outcome, I think, is critical. Certainly, the US has been outstanding at that. So mission-driven research has been going on for it's part of the lifeblood of the US. We've had collaborations with the US, and we've been funded by the US, and we've certainly learned from that, and we see that as very positive. I think the kind of aspect that the Australian psychology brings to that is the highly collaborative spirit and the openness to the world. So because of our nature, we're a long way from everywhere. We're used to collaborating. We've learned to do that very effectively. And I think with a field like this, that collaboration will be a critical component going forwards.
One, I want to follow up on that, but also want to ask a question. How much of this is needed, do we need advances in computer science to sort of come up with a new way of thinking about CS as opposed to kind of chemical and engineering and physics? In other words, this first computer was pretty worthless unless you had some kind of I/O and software to be able to make it all work. Yeah,
that's definitely the case. So at the moment there are hardware companies and software companies. Some hardware companies are bringing it in-house, but the software is going to be very different to existing classical software. So there will need to be experts in that area, and we're certainly training them in-house and working with others that have that expertise. That will continue to grow, but that actually highlights an issue that I'm very worried about, certainly in Australia, and that is the fact that a lot of students coming through now are moving away from computer science, and pretty much everything we do involves a huge amount of coding. And so I'm very aware that the future of all these high technology spaces requires young people that are willing and adept at coding.
So I want to ask you about that, but another question is, to what extent do you think the leading CS departments in the world are having classes on quantum coding?
So I think that's changing. So it used to be that there wasn't. Really now I think internationally what we're seeing is lots of countries, lots of universities are coming up with their own quantum courses, transitional courses to take it from a physics degree, a transition into quantum, taking computer scientists into quantum. So, the kind of degree that I tell young people, if you want to, be really well situated for the future, physics and computing is ideal. There's going to be huge jobs in that in the future.
It's like in the movie The Graduate when he advised Dustin Hoffman to go into plastics. So your advice would be quantum and software.
Quantum and software, yeah. Physics and software.
I'm surprised to hear you say that there are fewer graduates in CS, because at least in the U.S., CS graduates kind of peaked in the 2000-ish bubble, if you will. and they went down, and now they're coming back up and are up. We still have problems in the U.S. We haven't expanded our CS slots enough in colleges. There's more demand for those slots than there's supply. Yeah. There's a new report coming out in, I believe, this week or next week by, Code for America, on looking at what's happened in U.S. high schools, where we've made progress, but there's still a long way to go. I mean, most high schools in the U.S. still don't teach computer science, and some of the ones that teach it pretty basic coding kind of thing. Yeah. How do you see that playing out in Australia?
So look, it's a mixture. I'll be honest. We've got at the university I'm at, we've got a company called Glassman that's come out, which is a very heavy software company. They've realised that there's a huge talent pool in Australia, so they've benefited from that. It's a very successful software company. But going forwards, just looking at the students that come through the science degrees, we're recognising that they're not trained in coding, and so we're having to spend time training them. We're hiring a lot of people out of computer science departments. But going forwards, if you look at young people and you talk about coding, it's not something they think is fantastic. And actually, I think it should be inherent in their language. So for me, it's like another language they should all learn, and it should be compulsory. Certainly pushing for that in Australia. Other countries have gone that way. So the UK has gone that way. Singapore, sure. Lots of European countries. I think it's essential, and I think we've got to get onto that pretty quick.
Yeah. No, UK. I mean, Singapore's always amazing when it comes to this stuff. They're usually ahead of everybody. But the UK is pretty amazing. They've really pushed this into high schools now in a serious way.
They have. So lots of programs in the UK to get the young people into coding from primary school, actually. They're going all the way down to primary.
I want to come back to that in the context of girls and women, which I want to close with. But I do want to talk about collaboration. Obviously, the big innovation policy question today is U.S.-China competition, particularly in advanced technologies, semiconductors, and AI, and obviously quantum. The U.S. passed what was called FIRMA, which was our new export control and inward investment restrictions. So it's going to be harder for collaboration between the U.S. and China. Which, in my view, is probably a good thing. I'm curious how you see that in Australia and the science community in general. And then, related to that, would it be beneficial if there were sort of a Anglo-American collaboration? We take Europe and Canada. Obviously, we're joking about Prime Minister Trudeau being asked about quantum, and he sort of knew what it was, which was like how many. I guess your Prime Minister knows also about it too, which is unusual. But is that something you think is an interesting area to go down, a path to go down?
Yeah, look, I mean, we're situated very close to Asia, obviously in the Australasia Pacific, and so we do get to see the dramatic changes that are occurring there, the huge investment that's going in the quantum space all across the Asian countries. Like I said, we've typically been very good at collaborating across the world. US is our primary partner, and the UK would be our two primary partners, and I think strengthening that is only beneficial. I think we've learnt from the positives of the US about being mission-driven research. We're looking at the long-term applications in that space, and the US would be our natural partner for that kind of research. So I definitely think strengthening that over the future is good. Yeah. Canada obviously has a very strong program. The UK has a very strong program. So there's natural allegiances where people have been moving through those countries for decades,
Sure.
naturally collaborating with each other. And I see that as very positive. But one of the great things about Australia is we are close to Asia Pacific, so we've got a very good insight into what's happening there. And we do have students going back and forth at the undergraduate level with those countries. So it's quite, it's a unique position to be in, to see how the world is dramatically changing. But the strong alliance with the US, I think, is critical. Yeah.
I mean, we talk about that, and there are programs. NIST has an international program, NSF has one, but they're not, in my view, they're not as systematic as we could have. They're not strategic, and maybe that's the next step.
Yeah, I mean, so we certainly, I think from Australia for a long time, we've been talking with the US about, we have a Centre of Excellence model. We'd love it if there was an equivalent model. I know there are certain types of model like that over here, and that would allow us to collaborate a lot more strongly. So certainly at the moment, individual investigators will collaborate with individual US investigators, but there's a lot of overhead costs in the universities negotiating the legal documents and ITAR and everything else, so it makes it prohibitive You know, so
Yeah.
the researchers will naturally do it.
Yeah.
But making it official and actually co-funding to do things together is
Yeah.
actually quite difficult. So
Yeah.
we would very much welcome situations where we could collaborate on a kind of equal footing.
Yeah.
I think what we used to joke, both of us had at one point, I think the NSF and the Australian Research Council tried to get grants together, and they ranked them individually in each country, and the rankings were different, and then that was it. They didn't know what to do, and the grants never came out.
Let me guess, the Australian ones were ranked higher in Australia.
No, I actually think each other's.
Oh, interesting.
Yeah.
Interesting.
So that's interesting, yeah. So, but anyway, there's things like that
Grass
have
is
to be
always
worked
greener.
out. But yeah, collaboration ultimately, if the benefits for both sides, people will go through the pain to get there, yeah? And I think in this field, there is a lot to be gained from working together, and I think people will suffer whatever pain to get there.
Well, but yeah, one of the roles of government is to provide incentives to do that, and then reduce the barriers.
Absolutely,
And,
that would be great.
yeah, I don't think we have this program. It's been around since the 80s, the Engineering Research Center program at NSF, and I'm 99% sure they don't have a quantum center. We have things at Oak Ridge and things like that, but I don't know that we have a university one. There may be folks in the audience who know that as we get into it. So let me maybe just my last set of questions really before we open it up to folks. Oh, I know one question. When we were talking earlier before the session, we were talking about whether these things are going to be in mobile portable devices like this, or a little robot. And view was when you get to like just a teeny bit above absolute zero, it's going to be, God, my phone is freezing cold. I can't. So it's going to be sort of stationary devices for at least the foreseeable future. But I don't want to put you on the spot, but any sort of guesstimate when you think kind of we would start to see deployment of usable quantum computers in big organizations like insurance companies and pharmaceutical companies and aerospace companies and the like?
So look, I think it's really going to mimic the classical computing world where you have a server farm and people will access it. And certainly that's where a lot of the American companies are going. So IBM, Rigetti, Google, they're all making their systems available online, so open access, that you can go and try them out. And I think that's the way I see it, certainly for the next decade. It's difficult to predict because so much technology has to evolve, but I don't see it being portable in the next 20 years.
But it wouldn't. That's an interesting point, because in the old model, with mainframes, you'd have a mainframe somewhere, and then they still have mainframes, but now there's a lot more done in the cloud, and there's lots and lots of algorithms that make that work. So do you think that sort of the cloud quantum?
That's exactly the model that a lot of companies are following. And so then the question is, how do you work with the end user? Ideally, they have to be integrated enough that you understand their problem and they understand how it works. So if you're too remote, then they're going to send things, they're going to get stuff back, and no one's going to know why it's not working in the way they expect, and they're not really sure what to expect from it. So there has to be quite a tight link at the beginning with the end user and the hardware.
All right, so here's my ignorant question. What is quantum communications, and do you need that to make cloud quantum work?
Yeah, well, that's a good question. So at the moment, quantum communication is where you can transmit information absolutely securely. So you're transmitting in a quantum state, and if somebody hacks into it, the state destroys itself. So you can only get it if you have the quantum key. So China has invested heavily in this area with their satellite systems. So it's called absolutely secure communication. Ultimately, any data you send, people can hack into, theoretically at the moment, depending on how well it's encrypted and protected. So the quantum communication promises absolutely secure communication.
Even not unbreakable by a quantum computer?
So unless you potentially have a quantum computer, but even then, there's a big debate about that. So people are trying to develop quantum communications against classical hacking. So that's what it is in the first instance. So you won't be able to break into the existing systems, and then quantum computers promise all kinds of new technology beyond that. But they essentially go hand in hand. So the kind of utopic view is secure communication systems with processors that are quantum and information transfer, which is quantum. Okay.
All right. So I want to just spend a few minutes on this other issue that I know you've been quite active in and taking a leadership role in, and that's more girls and women in STEM. In the U.S., we did a report on this a while back, and fairly high share of women in bio and life sciences fields, but when you get into engineering, it goes way down. CS is a little bit better than engineering. There are lots of different models of this. One study that we cited was that young women when they go to college. Well, this is true for boys and men as well. There's a lot of weed out that they don't have enough slots, and so they force people out. At least they do this in the U.S. It's very common to have a weed out process in engineering. Partly that's because they don't have enough slots, because the government, they can't fire the French teachers, and so and then hire the engineering professors. But anyway, one of the interesting things is the women who leave are actually, if you compare their scores, and they're actually slightly better than the women who stay. So it's not like we're weeding out the poor students. We're actually, for females in the U.S., we're weeding out the better students. So part of it is not that there aren't enough women in the pipeline, although that's an issue as well. It's partly how welcoming we are in that process. And then you have places like Carnegie Mellon, for example, which really revamped how they changed the acceptance process, and not to dilute the thing, but to just look at different characteristics of what the students were getting, and they were able to improve their enrollment rate of females by a significant amount. I'm going to get the numbers wrong. Went from like 20 to 40% for CS. And then in the U.S. we have this model, which I'm a huge fan of, these specialty math and science high schools, where we have over 100 of them. And one of the really interesting things about them is that the share of females, girls in those, is very, very high. And the girls do very, very well. I was talking to a principal in one of the schools, and she was telling me one of the reasons girls do well there is because the expectation is for them to be smart. There's no sort of social stigma to not be smart, and so it's just like, you're a girl, you're going to compete with the boys, and you're going to be as smart as you can. And that's, I think sometimes in regular high schools, at least in the U.S., there's this view that maybe you shouldn't do that.
Yeah.
So I'm just curious how you see this in Australia, how it's playing out, what are the kinds of things that policymakers are trying to do to fix it?
Yeah, look, I think it's a big issue in Australia in terms of, in a different way. It is actually the pipeline in Australia. So they've looked actually in the UK and Australia, the drop in females interested in the subjects like physics and computing occurs at the age of 15, 16, and it literally drops by half when they head off to university. And so there's a big drop at that level, and they're trying to figure out why it happens. And I guess one of the things we've been looking at, certainly in those countries, is that a lot of females can't see their career path in the future. So if I do physics and computing, what kind of job am I going to have? And there's very few kind of role models in those different areas that they can relate to. And so that's what we're identifying as the big issue over there.
Is that they can't see, because they can't see the path, or they just sort of can't see themselves in the path because there are not enough role models who are the same gender?
I think it's both, but primarily they can't see the path. So literally, we've looked at what teachers and careers advisors are telling students at high school level, and they're really saying to them, if you get a job as a lawyer or a doctor, it's kind of safe, you know what you're going to do. If you go in those other areas, we don't really know what you'll end up doing. And of course, if you've got a child choosing and a parent that's very keen to know that their child's on a nice pathway, that all influences them.
So let me just sort of push back a bit. Why is that different for boys than it is for girls?
I think in terms of looking at
risk
role
taking?
Models, there are very few female role models.
Okay.
So they can't see they can't see, if I do that, I'm going to be like this person.
Sure.
So I think that's part of the issue. So we're looking at processes in Australia about highlighting the role models in those different areas. So whether it be an engineer at Qantas, or whether it be one of these quants in the bank, or whether it's somebody working for Atlassian, the software company. So we're going out there now and highlighting these are the kind of jobs you can have, and actually putting the emphasis on the skills, and saying, nowadays jobs change so quickly. Don't set yourself on a path where you're stuck in one career. Actually, you're going to be changing multiple times. So the key thing you've got to do is get the skills that open up your world, rather than choose a job that shuts down your world. And so we're really going on skills, encouraging them to look at things like coding, look at whatever things they enjoy and build the skill sets around the things they love, but then highlight the careers that are out there and show the diversity, if you do hard science subjects, where they lead to. So
how much of this also is, I don't get in big trouble for gender stereotypes, but how much of this is, do you think that girls or young women think science is isolated and it's I don't want to just never talk to people, and some science is more like that than other science. How much of it is explaining to girls or young women that there's you're doing science, but it can be quite collaborative and teamwork?
Yeah, I think that's true. I think all of those things are true. Yeah. So looking at the stereotypes that are out there, they're not very appealing for young girls, and there are other things that are more appealing. So, finding those people that are doing well, enthusiastic, passionate about their fields, that have enjoyed those areas is something we're really trying to focus on.
Yeah. One of the interesting studies in the U.S. was that female graduate students, on average, not everybody, but on average, are more attracted to interdisciplinary research than males. And when you fund, there's a program called IGERT, Interdisciplinary Graduate Education and Research, something like that, out of NSF. And it turns out that program is really, really effective at getting women to stay in, to get in graduate programs, to stay in and graduate, because they're seeing it's not just one narrow thing, it's much more interdisciplinary.
Yeah. Well, look, I think that's the case. It's always dangerous to generalize,
sure,
because you know, the world has evolved the way it has under the conditions it's evolved. And I think if you look at now, you know, there are very few science teachers, particularly in Australia, that are female in the physics space. So, you know, if you start to change that up, you change what young people are exposed to, it will eventually, things will evolve in a different way. And so, but yeah, it's too soon to know why things are the way they are, but it is not too soon to start to change it, I think. So.
We were chatting about this great podcast from Australian broadcasting company, I guess, ABC, called Fierce Girls, and I listened to it with my 12-year-old daughter, who just adores it. But it's all about Australian women who've overcome the odds and done great things, like Kathy Freeman, I guess, the runner, and other people. But so far, there have been no scientists on that, so
we've changed that.
Something Australia should fix. Put 3 or 4 women scientists in there. So why don't we open up for questions? If you can wait till the mic comes around. So if you can identify who you are and who you're with, and then we'll go from there.
Great. I'm Ami Taibanan, with a former physicist, and now I do autonomous vehicle work at SAFE, which is a think tank in DC. I wanted to ask you, there's a lot of innovation going on in the classical semiconductor architecture. Now, we've seen a lot of emphasis on GPUs, and now we're seeing the emergence of TPUs and other ISACs, so new architectures that are emerging for specific tasks that are promising multiple orders of magnitude of speed-ups. How do you situate quantum computing within that innovation? And if you're either a deployer of capital or a company, how do you decide to invest in either speed-ups of classical architectures or more targeted classical architectures, or quantum computation?
So I guess if you're looking forwards, you would bet on both, because the classical computing world has been phenomenal, and it's going to keep going. It's not going to stop. So I certainly would not suggest everyone switches to quantum. But at the same time, there are these new capabilities in quantum that you just don't get. So at the moment, I think people that are in the quantum computing field feel that it's inevitable. It's going to happen. We can't predict how quickly, and we can't predict what are going to be the commercial applications in the short term. But our view is it's going to happen. So I think if I was investing, I'd go both ways.
Yeah, we always underestimate these technologies. The famous line we were talking about of Thomas Watson, the head of IBM, predicted that I think the worldwide market for mainframes would be, 15 or 20 or something like that. So.
Hello, Eugene O'Brien, AARP. Thank you so much for your presentation. It was just really informative. I'm currently fixated on the competition between China, the United States, and the Western worlds. How do you see the availability of talent in China versus the rest of the world, the young scientists that are coming out, and also the funding with quantum computing, the availability that the government of China may be underwriting the various companies and that? Are we far behind, or in terms of the inevitable competition, or are we keeping pace? Thank you.
Okay, it's an interesting question. So for me, we've been working with the US with collaborative programs since 1999. We've been funded by the US Army, and so I've seen the incredible depth of knowledge and innovation in the quantum computing space in the US. So I wouldn't be concerned that the US is behind in any way. I guess it's primarily been in the space of the defense agencies, and now it's coming out to NSF and other agencies along the way. So that's the kind of transition I see. But certainly the depth of knowledge here is incredible. So at the same time, China has a huge population, and they're putting lots of money in it. And I think they're putting money in it because they recognise it's the technology of the future, and they want to be, one of the world leaders in it. But at the end of the day, I think lots of different countries are investing because they believe in the technology. No one knows what's going to work at this stage, and I think the US are in a good position because they got in right at the beginning. I think Australia's in a good position. It invested in its centres of excellence back in 2000. So we started those programs 20 years ago. And so, at the moment we're sitting in good positions. I think the Australian team has focused on one particular area they're very strong in. And I think the size of the country has, it can't do lots of different types of quantum computing. So I think Australia's in a very nice position, and that relationship with the US is very strong. So,
Do you think with the 5 different I think you said there are 5 different major architectures.
5 that have companies at the moment. So
Pardon?
there are many more beyond that, but 5 that actually have companies that are pushing the application space.
But there are even more architectures. Yeah.
I think there are, but I wouldn't necessarily put them in the commercial space. That's
Sure.
That's the
Sure.
thing.
Because historically, in technology, they tend to narrow pretty quickly, and we had germanium versus silicon. That only lasted 10 years, and
Yeah.
Intel bet on silicon, and Fairchild bet on germanium, and that's the end of the story. Do you think that there's going to be a shakeout sooner rather than later, or is it just we just don't know enough, and it's just going to keep kind of going on different paths? And
Look, I think we don't know enough, and the reason is we're encoding in completely different states, whether it's spins or whether it's photons of light or whether it's flux qubits. They're completely different states of matter that we're encoding on.
Okay.
And so it's just not known at this stage which one is going to have the long-term benefit. Yeah? And so, each one of you, I could give a story why you should invest in that and not
Sure.
anything else.
Yeah.
So it's a pretty level playing field, but I think at the end of the day you've got to look at what can actually make a product sooner, because then you've got to test what it can do sooner. And so those and the materials that are more advanced, which is why I think silicon's so exciting.
Yeah.
It's had a huge amount of infrastructure over the last 50 years, and we're piggybacking off that to push to an application quicker.
Do you think is there a risk that a government would bet on the wrong horse? I mean, I haven't looked at what the European Commission is doing yet.
So the EU has got a big program again. It's a lot of money, but it's spread across all those different implementations. The US has all those implementations already funded in different schemes. So I guess just the Australian equivalent, we can't fund all of those at the same level.
You got to.
So we've got to choose.
Got to do one, absolutely.
Choose one, or maybe arguably people say there's 2 or 3 underway in Australia at the moment. So. But so it's a very interesting field. It really isn't known, and I think at the end of the day, you may end up with different types of quantum computer.
Sure.
And some may be faster and do certain types of problems. Others might do more different types of problems, different simulation problems, as opposed to full-on universal computing. So it's just not known.
Sort of to this gentleman's point about silicon sort of going down that path. Now you've got certain silicon that's optimized for vision and machine learning, and others that's optimized more for classical processing. Maybe that's what might happen.
Yeah.
Okay. Right here, Josh.
Josh, HIF's Center for Data Innovation. So earlier this month, there's a quantum computing startup called Rigetti, and they announced what they're calling like a hybrid quantum service. I don't really know if that's just clever branding, but they're really talking up the value in having a really tight interplay between traditional computing and quantum computing, dividing workloads to make quantum computing more practical. Could you just describe how that process works a little bit, and how do you see that interplay changing as quantum becomes more powerful and more feasible in the future?
Sure. So obviously I don't know the ins and outs of the Rigetti system, but I do know that at the end of the day there are some problems that a quantum computer is adept at dealing with, and some that it's useless at. And so ideally you want to be able to figure out which problems when they come in are going to go to the quantum part of the chip and which are going to go to the classical part of the chip. And so the kind of utopic view is you'd have them kind of co-located, and you'd have ways of defining the problem as it comes in as to which part it goes to. And so that, I think, is that kind of hybrid model is kind of what everyone's doing anyway. In order to run the quantum chip, you need a lot of classical control, and that computer itself is a classical computer attached to your quantum chip. And so at the end of the day, there's a huge amount of research in that space about how do you define the problem, which way does it go. And I think all hardware companies are doing the same thing, because they have to optimize the quantum chip and what they send to it.
So we'll never be in a time where it's just quantum computing.
No. No, never. They'll always be together. It's certainly in the foreseeable future. I don't see it changing. So, if you're thinking about it in our space, you've got an atom, you're trying to get information on and off an atom. You've got to do it quickly. You've got to interact it to do the operations. All of that is going through, at the moment, electronics, which is classically controlled. That's why I say coding is so important. Everything we do is coding the operation of the actual dilution fridge, the coding of the actual electronic equipment, the coding of the manufacturing equipment we use to make it. Everything is coding, and it all requires classical control of the quantum states at the end of the day.
Right here, and then in the front again.
Hi, I'm Naomi Weber with Lewis Burke Associates. We work with a number of universities, and a lot of the people I talk to in quantum are all men. So I was wondering how many people, what was the balance at the White House event you went to yesterday? Were you the only female?
Actually, I never looked. I think there was a very small percentage of females in the room, yeah.
Is that different, would you say, in the US compared to Australia?
No.
That's
true all over the world. Actually, the few females in the quantum space, we know each other pretty well. We get asked to lots of events, but yeah.
Is it more pronounced in quantum than physics overall?
I think it is. So certainly astronomy has gone much more balanced.
Yeah.
Condensed matter, I guess a lot of us have come from a kind of condensed matter solid state background. That was always pretty low, but I think it's something like 5% of physicists, quantum physicists, are female. Condensed matter may have been 15%, so it does seem to be very small.
Interesting.
And actually, to be honest, for me, when I talk to young girls, I tell them the tremendous opportunity in that space. And really, one of the things I try and highlight to them is there's this new wave of technology that's coming. If they don't skill up, they're going to miss it. And so don't miss out, because it's really fantastic. It's a lot of fun. It's very rewarding. So it is fun. Honestly, it is.
Now, my son, who's studying computer science, he has this view of the world that he missed, like the golden age of 1994. And I keep telling him, don't worry, there's another golden age coming up, and you can be right in it.
Because I got so fascinated looking at the classical industry, I really think, God, I wish I was there at that time.
Yeah.
It's such a fantastic industry. And then every now and again I say, actually, we're in
You're
that
here.
next-
You're
we're in it now.
You're there now.
So we must be careful. Keep looking over the fence. You've got to enjoy where you are.
Yeah. So, yes, sir.
Well, thanks for your indulgence. So I think there's been a structural change in how companies have approached R&D in the U.S. Now, since the 60s and 70s, where there's been less of a focus on exploratory research and early stage research, especially outside the tech industry, and I think some of your slides reminded me of that, because you showed some of the advances in semiconductors that were done at Bell Labs in the private sector, whereas a lot of the activity you're showing today is consortium activities between government, industry, and academia. Not to wax nostalgically about a bygone past, but are there any inefficiencies? Is it more difficult to operate in a role where you're trying to bifurcate work or cooperate across sectors to do work, or do you think that's actually a more advantageous way to do it? Or if we were policymakers thinking about how we want to structure R&D, should we be thinking more? How should we be thinking about cross-sector collaboration?
Yeah, I think that's a great question, because again, I can only come back to my own experience, but in Australia, it's a small country, so those different agencies work together. So universities are close to industry and closer to government. We just see each other more. And so creating a structure where they're all co-investing was not easy to do, but it's possible. I think in the US, you've got big agencies, lots of different big agencies, sometimes in competition with each other, universities in competition with each other. And so to get the best out of the US system, ideally you'd all figure out like a common ground. I don't know how easy that is, but that would be something that's highly beneficial. And if you've got companies coming out in the space that could potentially be taking too much talent out of the universities, then the university research sector is going to suffer. And so there's all kinds of challenges over here that I can see evolving. But this initiative from the government is really about pulling all that together and making sure that all those agencies are talking and figuring out how to optimize the system here. So I think it's a great announcement, and certainly from the Australian side, we welcome that announcement because we're looking forward to continuing to work with the US.
Yeah, just on that point, I was struck in your slide about I guess the provincial government, the state government in Australia, and then also it said innovation agency. I don't know, is that the national agency? Did equity?
So it's the actual Commonwealth government and then the state government. and then it's university, and then
Yeah.
companies.
Yeah. So in the U.S., that's probably, I don't want to say unprecedented. We have InQtel from the CIA that gives some equity. But by and large, our government doesn't give equity, which I think is a mistake, frankly. We should just have all sorts of different models. But why politically can your government do an equity investment? And I think it's not like a diluted equity investment. It's a real equity investment.
Yeah. Look, I think, so we looked at the Australian system, and it is very different to the US. We have a very, very strong research base, but we don't have a lot of companies, so we're geographically dispersed from the rest of the world, so that's very tough for us. And so as a consequence, we can build, and we have done over the last 20 years, huge research expertise in certain areas. And so the government was really looking, how do we capture that economic benefit in the long term for Australia? And so that co-investment came about from a very long-term strategic play in a technology they think is going to come to fruition. And so it's really, looking at the benefit for Australia. That's the argument that we came about with.
And how long has that program been in existence, approximately?
Well, so it started really back in 2013 with the Commonwealth Bank funding the university, and then over a period of time we've had co-investment from government in terms of research up to that point. But then the company started about a year ago, but it took about 3 years to get to the point where the company could start.
Okay. So it's too early to know whether the government's going to ever make any money off of that overall program. You assume that they're going to, if they have any sort of, commonality with venture, 1 out of 10 will work, and they'll make a lot of money and support the fund in perpetuity.
Yeah, I think it's too early to say, but I guess one of the things that's happening in Australia is it's kind of kick-started the whole ecosystem. So the whole quantum field in Australia is getting stronger and stronger. There's investment coming from overseas. Lots of companies have now started to come out in the quantum space in Australia, and that was, it was kind of a kickstart for the whole ecosystem.
Interesting. So who in government sort of figured this out? I mean, not like figured out technically, but sort of came up and said, we think there's some space for Australia and we want to be helping.
I think it's bottom-up driven, so it's been a mixture of the research agency looking at their Centre of Excellence model. They basically, it's a triangular system, the Centre of Excellence at the top. This has been the only centre in Australia that's got a third Centre of Excellence. They're a 7-year funding program, roughly about $7 million a year. And so they've recognised, we've funded this for a long enough time now, it's got all these patents around it, we want to push it to the next level. What kind of scheme can we do? So it's been a kind of government, research council, university-driven process about what's best for Australia.
Okay. Other questions? There's another one I wanted to ask, which is two more that I wanted to ask. One is you had a slide on there about autonomous vehicles and using this for that. So explain to me, you obviously can't put a quantum computer in a car and I'm going to avoid hitting a dog. But they're using it to model, and then on the basis of that modeling, that's going to improve the algorithm in the car. Is that how that would work?
So at the moment, honestly, I don't know how they're doing it, because again, it's all done by the company directly.
Yeah.
So that we just know that Google are investing, and that's one of the areas they're interested in.
Oh, okay.
So the actual practical application, I don't know of how they're actually imposing that. But I guess anything where there's huge amounts of data and they're looking at pattern recognition, the more powerful the computer you've got, the faster that's going to be.
But then, but how do you then translate? Maybe you don't know. That's fine.
I don't know.
Okay.
So how do they translate it real time? I don't know.
Translating it back to the actual car to be able to recognize it.
Right.
Maybe you know that. I don't know. No.
Oh, I mean, I'm assuming it's done on the where you,
My sense it's done on the data training side.
Yeah.
Sure.
Right, because you're fusing together multiple data sets of real world experience, whether it's people's locations from your Waze database with hours of video from your vehicles that are on the road. I actually was going to ask a follow-up question, but
Sure, ahead.
Sure. So actually, I wanted to follow up. I asked you before about innovations in conventional silicon, and I just so I wanted to follow up and ask you: should I be thinking of quantum computing as an ASIC, as a specialized piece of hardware to do the algorithms in the quantum zoo, or is it something more fundamental than that?
That's a great question. I don't know how to answer that, because in my mind, that is a way of looking at it, and it's a valid way of looking at it. But in my mind, I guess it's going to open up applications that we can't see, and the bigger the quantum system, the more the applications. So it's almost like it is almost like an independent piece of hardware at this stage. Mm-hmm. So I can see that view. And that is a way that you could look at it. But for that field to grow, there has to be sufficient investment in looking at what's classical, what's quantum.
So let me ask, so we're 25 years after Peter Shor, and we're sitting at, you said 50 algorithms in the quantum zoo.
Yeah.
So does that suggest that quantum computing is a general purpose technology, or is it just it's a very specialized technology?
So, at the beginning of all classical computing, the hardware was built for a particular problem. I think you're going to have exactly the same in the quantum space. It's going to be built to address a particular algorithm at this point, and eventually we're going to get big enough that we can make them universal. That's the hope. But we're really at the early stages at the moment.
So I want to ask a related question, and you can jump back in if you want. It strikes me that when you did the thing where the atom can be either up or down, and here it can be in multiple things, and then you put the two together, and that what we're really talking about is sort of infinite amount of computing in a way, and if you think about data in the world, there's really an infinite amount of data in the world. It's just if we could measure how each fiber in this carpet is right now. I mean, in theory, you could do that. You could measure each molecule in the air. You could measure everything. And I think we're moving to a world where we're going to be measuring many, many more things. Like orders of magnitude more things will be measured.
Yeah.
And do you think that's sort of that and quantum kind of go together? Like the more we measure, we'll be able to process it better, and the better we can process it with quantum, the more we're going to want to measure, and sort of the data and quantum explosion go together?
In some ways I do see they go together, but you've got to put the caveats on there. If you look at a classical computer at the moment, it can only model about 20 atoms. If you make something bigger than that, it falls over you. And so there's a limit of how efficient a classical computer is to model as a quantum system. And so there's going to be a level of which we can, build the quantum system big enough that we'll be able to do those kind of calculations. But at the same time, we've still got to get data in and out of this quantum system. So there's all kinds of challenges about the classical flow of information to the quantum state, as well as the operation of the quantum state itself. Yeah. So that's why I guess I'm trying to put that in context. It's not something that's going to happen overnight. It's something that's going to take a lot of development in the software space, in the interface with the classical control systems, and in the actual quantum algorithms that we can run. So in every aspect of this is pushing the boundaries of what we currently know. That's why it's hugely exciting, but that's also trying to temper that with there's not going to be a commercial device that's going to solve problems in 5 years that everyone's going to want on their desk. It's a very different field.
Right. And also, we were talking earlier, I don't know if I mentioned, I finished reading this new biography of Andy Grove this summer, which if you haven't read it, I highly encourage you to read it. It's about a fascinating 700-page book, and it's just, it's really, really interesting. But one of the points that you really understand from when Intel back in the, I guess it was started in the early 60s, I guess, or that it wasn't like they had one problem they had to solve. They had 30 problems they had to solve. And each one was a gate. If they couldn't solve that problem, they couldn't. So it sounds like what you're saying is similar to that there's just a massive number of problems to solve. And solving them all gets us a lot of progress, not just in the narrow space of quantum.
Absolutely. One of the things, again, looking at the way Moore's law evolved and the kind of roadmap the semiconductor industry had, was it mapped out all of those problems. It was very open about the problems. And then people addressed them. And so that's, part of the challenge now is getting a big enough team to address all the issues you know about, but then that everything's always improving. And so, that's why I say it's a field that you'll see, you get a big enough team, suddenly you start to get momentum in that team. And that's really what you're seeing now in the quantum space. That momentum is coming from lots of different teams across the world that have built to that capacity.
Interesting. So I don't know where we are on that, but we have had a roadmap, as you mentioned, through the Semiconductor Research Corporation for many, many, many years, and co-funded with the U.S. government. And then it basically said, how do we get to where we need to go in 10 or 15 years, and what are the barriers, and how do we get our scientific teams to work on that? Do we have a quantum roadmap? And if not, should we have a quantum roadmap? And if we should, how do we do it?
So again, that comes back to this, I showed you the 5 different implementations. They've all got their own roadmaps,
Okay.
So put it that way, I would hope they all have their own roadmap. Okay. We certainly in Silicon have got our own roadmap, which we worked out for, a long period ahead. But I think it's a necessity to get one for any group that's working in this space. There isn't a communal one. There was
That's my point.
There was 5 to 10 years ago an attempt to get a communal one, but they realized it was too soon.
Yeah.
And there's too many different kinds of problems, too many different implementations, so it didn't
Yeah.
really make sense.
Yeah.
But there, I'm sure if you go on the web, you can put quantum roadmap, you'll probably find people have tried it.
All right.
But not in a coordinated way for each individual implementation.
Yeah, I mean that was I think the unique thing about what the SRC did. It was a very you had Intel and IBM and other HP and number, and then the leading scientists and institutions.
Yeah.
Okay. Okay. Any last comments or questions? Okay. So first of all, I want to thank you all for coming. This, by the way, for your friends who want to watch this will be up on our website probably tomorrow for the video feed. And then thank Professor Simmons for what you're doing. It's great. And
Pleasure.
Congratulations, by the way, on Australian of the Year, which I understand does not come with any money, but only comes with fame. And so,
Thank you.
thank you. Great. Thank you.